Okay, so 164 gram piece of copper is placed into water at 20 degrees Celsius. They come to equilibrium at 24 degrees Celsius. So they've already solved the calorimetry problem for us, right? And so we're going to do the entropy change of the copper, of the water, and then the total entropy change. Okay, so the first thing I'm going to do is I'm going to figure out the Q of the Q, the absolute value of the Q, right? So that's going to be MCAT, the absolute value of our temperature change, right? So that is 0.164 kilograms, right, times 390 times, it goes from 32 to 24, right? So it actually went down 8, but I'm just going to put in 8 to get the absolute value of our heat flow. So 0.164 times 390 times 8, 511.68. That's our Q, right? That's the heat that flows, right? Now for the water, that's going to be a positive, right? And for the copper, it'll be negative because the copper loses the heat, right? But now the next thing we want to do is we want to figure out the average temperature of these things, right? Because we are estimating. Okay, so for the copper, the average temperature would be the average of 32 and 24. This is higher math, so I've got to use my calculator. And then divided by 2, that is 28, right? So for the copper, the average temperature is 28 degrees Celsius. Now this is, by the way, a fairly large change, and so our estimate is going to be pretty estimating. Okay, for the water, it's easy. It's 20 to 24, so the average is 22. Right. Okay. So now let's figure out the copper. Let's go. Here we go. Okay. So for the copper, our change in entropy is Q over T, right? So it's minus 511.68 joules, right? Divided by, and then its average temperature for the copper is 273.15 plus 28. Okay, and this will be a negative change. So let's go negative 511.68 divided by parentheses 273.15 plus 28. And that is negative 1.6990868, etc., right, joules per Kelvin. Okay, and that's for the copper. Okay, so now let's do for the water. For the water, okay, our delta S is Q over temperature, right? And so the water gains the heat. So it's going to be a positive change, right? And then this is 273. Now notice that the cooler thing is going to have a smaller denominator, therefore there's going to be a bigger change in entropy, a bigger positive change. Okay, so the water, the average temperature was 22, so we go 511.68 divided by parentheses 273.15 plus, all right, moving the chairs around up there. All right, 1.7336, positive 1.7336269 joules per Kelvin. Now notice this will always be the case when heat flows from hot to cold. Okay, the decrease of the hot thing's entropy will always be smaller than the increase of the cold thing's entropy, and that's because of this denominator, right? Hot things have a bigger denominator, therefore it's a smaller change in entropy. Okay, now if we combine these two, okay, if we, let's store that in B, and then let's go. Store that in A, and then I go alpha A plus alpha B. I get, if I combine those two, right, the net change is positive 0.03454 joules per Kelvin. There's a net increase of entropy. Yeah, there we go. think that's all you need to say about that.